Hello friends, welcome to video lecture on dynamics of machinery. In the today's lecture, we'll discuss about numericals on equivalent single degree of freedom system, session 7. So let us start the next problem. A heavy door along with a door closing system is as shown in figure. The moment of inertia of the door panel about the hinge axis is 20 kilogram meter square and the stiffness of the torsional spring is 25 Newton meter per radian. Find the most suitable value of the damping coefficient. Neglect the effect of inclination of the dashpot axis when the door is open. Now the system is given like this one. So just let us imagine that. So this indicate a door. Okay. So towards the left side of this door, this one a spiral spring is attached. Okay. So at the back side of this one damper is attached. Okay. When any person try to open this door, okay, in this way, okay, then the tendency of this spring to compress, okay, and at the same time the damper moves in forward direction like this one. Okay, when we release this door, the tendency of this door to regain its original position. Okay, because of whatever the energy stored in the spring, okay, the compression of the spring is converted now into expansion. Okay, now say, as per our earlier discussion, first of all we have to draw the free body diagram or displaced diagram of the given system. When I pull this door in, right now in this case in upward direction like this one, now see the forces acting at a various portion of this system. So here this force is nothing but the spring force, okay, kt into theta. Okay, so I can say the theta. So let the door is displaced. Let us consider this door is displaced by angle theta. Okay, so the torsional spring deflated by an angle theta and a damper, this one is displaced by linear displacement or a distance x, such that we'll just say the relation here. So in this way we can found the relation between the linear displacement and angular displacement. So x equals to b into theta. So this distance indicate b. Okay, so this is the theta. So for the smaller displacement we found this one, x is here, theta is here, and this distance is nothing but the d distance. So you can get for the linear displacement, that is x equals to b into theta. So if I differentiate this x with respect to time in t, then you can find x single dot equals to b into theta single dot. So what's about this indicate? This is nothing but the spring force. Okay, so here the spring force equals to kt into theta. Okay, so what's about the damping force? So damping force in this case is nothing but, so this coefficient of damping is nothing but here c. So if I consider x is nothing but the displacement, so what's about the velocity? X single dot is nothing but the velocity. So product of this damping coefficient and velocity is nothing but the damping force. Okay, so c into x single dot equals to, so what's about this c into x single dot? Okay, so here already the relation for x single dot and this term with us. So simply just write here c, or replace this x single dot by this term b into theta single dot like this one. Now easily you can develop the differential equation for this system by using Newton's law of motion. Okay, so from the Newton's law of motion. So what's about the Newton's second law of motion? Accelerating force equals to summation of external forces. Okay, so accelerating force. So in this case, just focus on the various forces. When the system or this door is displaced in upward direction, so accelerating force comes in the direction of the motion of this door. So the magnitude for this one, I into theta double dot. What's about this rest of external forces? So spring force. So spring force comes in the reverse direction of the motion of this door. So what's about the value for the same kt into theta? So what's about the damping force? This also comes in the opposite direction of motion of this door. So accelerating force with us I into theta double dot. Okay. So what's about this one? This turns about this point in which direction? This one in anti-clockwise direction. So you need to consider this one as positive. Okay. And towards the this one kt into theta. Okay, kt into theta, this term will remains as it is because this actually turns about this center point. So kt into theta, this turns about this point in clockwise direction, so give the negative sign for the same. What's about the next one? C into x single dot. Okay, so you have to take the moment of this force, this one c into x single dot, about this point. Okay, so what's about this one? This distance with us 100, or before that distance, just consider this one is nothing but the b. Okay, so we can get the next force cx single dot multiplied by this distance with us b. Okay, so rearrange this equation in this way: I theta double dot plus, so what's about this one? X single dot already with us. Okay, just replace that x single dot by this term b into theta into single dot. Okay, so c x single dot means b into theta single dot, again multiply by this one b term. Okay, now this is about the this term, so take this term also towards the left side, so the equation will be modified like this. Now again simplify this equation: I theta double dot plus, now b multiplied by b is nothing but b square, so cb square into theta single dot plus kt into theta, like this one, equate with the 0. Now if you look towards this equation carefully, so what's about these terms? So first one, this term, the coefficient of this theta double dot is nothing but the mass term. So what's about this one? This is nothing but the damping term. So what's about this one? Stiffness term. Okay, so in this case if I just say the second term is nothing but the damping coefficient for the torsional system. Okay, so cb square is nothing but the ct. So rest of this term, this is nothing but the spring stiffness for the torsional spring, so this is nothing but the mass term. So in this case I can just simply write ct equals to cb square in this way. Now this equation number a equation with us, to represent this equation a as critical dam system. Okay, so for equation A to represent a critically damped system. So we know for the critical damped system, C is nothing but Cc. What's about the meaning for this one? Actual damping coefficient equals to critical damping damp coefficient. Okay, so simply here we can get the uh, this one, we can simply write this term with respect to torsional spring like this one, Cc into T. This indicate the damping coefficient for the torsional system. So we know the relation for this one, 2 into Kt into I. The same relation we have seen for the linear uh, systems. Okay, so Cc equals to 2 into square root of K into M. Already we have seen that equation. So what's about this one, CCT for the critical dam system? Just now I discussed the CCT, this one CCT in case of this one torsional system, CCT must be equals to C into T like this one. So CT term already with us, CT is nothing but CB square. So can we replace this CCT by CB square? So CB square equals to, okay, so what's about this one, CB square into 2 into square root of KT into I like this one. So what's about this C? C is nothing but 2 divided by B square into square root of KT into I. Already this terms with us, B divided by, sorry, 2 divided by B square. So B with us 100 mm. So convert this into meter by multiplying 10 raised to minus 3. So we can get the 0.1 square of this one multiplied by square root of KT. So what's about the value for the KT? Already given in the problem. So what's about the KT? 25 Newton meter per radian. This value with us. So 25 multiplied by, what's about the value for the I? I already given, moment of inertia 20 kilogram meter square. So substitute here, do the calculations and get the value for this one. C, instead of writing only C, I'll just give the suffix for this one as CT. Okay, just indicate the damping coefficient for the torsional system. Okay, so after doing calculation, we found the value for this CT equals to 44.136 Newton second per meter. Let us start with the next problem. Find the damping factor C of the damper shown in figure such that the system is critically damped. Use the following system specifications. R1 equals to 10 centimeter. So R1, okay, this distance is given 10 centimeter. Then R2 with us 30 centimeter. IP equals to 1.1 kilogram meter square. Okay, this indicate the moment of inertia for the given system. And then M1 with us 10 kilogram, this one. M2 with us 25 kilogram. K1 with us, so the stiffness for this spring is given. K1 equals to 10 raised to 4 Newton per meter. K2 equals to 10 raised to 5 Newton per meter. Okay, given. Then our aim is to find out the value for this one, damping coefficient C. So in this way the system is given. The system involve this one. Let us imagine that one pulley is given. Okay, so the pulley with us, so towards the one side of this one the mass and damper system is attached, and another end of this one the spring is attached. Okay, so on the inner step of that pulley one more mass along with this spring is attached. Okay, so let us imagine that to get the solution for the C, so displacement for this mass is given. Let us imagine that the mass is displaced, okay, by a distance x like this one. Okay, at the same time if the displacement given for this mass as the rope or this one the string is wrapped over the surface of this pulley, the whole system try to move into this direction, and if you just look towards this one, this will start moves in upward direction. Okay, let us consider that if the mass is this mass m1 is displaced by this one distance x, okay, as shown in figure, the pulley would be rotated by an angle theta. So in this case if you look towards this one, so what's about this indicate, this is nothing but the free body diagram for this given system. Okay, So when the mass is displaced by this distance x, the pulley is rotated by angular displacement, that is angle theta. This would be result in the mass m2 displacing by a distance x1. Let us imagine that the mass m2 is displaced by distance x1. The spring k1 is stretched by x, whereas the spring k2, this one k2 is stretched by x1. Okay, so the relation between this theta, x and x1 would be, so if you concentrate on this one x, okay, so because of the movement of this mass in downward direction, so what's about this one? This is nothing but the accelerating force because of this mass m1. This indicates the accelerating force because of the mass m2. So what's about this one? This indicates the accelerating force because of the motion of this pulley. Now see the direction of every mass shown here, accelerating force shown here. Okay, this will comes in the direction of motion of that particular uh, mass. Okay, so this mass moves in downward direction, so of course the accelerating force comes in the direction of the motion of the mass. So this mass moves in upward direction, so accelerating force here shown in upward direction. Okay, now what's about the rest of the forces? So this one, if this mass moves in downward direction, the tendency of this damper to resist that motion, so the damping force comes in opposite direction of this motion. Okay, so that's why this one shown in upward direction with the magnitude here k into x single dot. Okay, similarly towards this side, so if this moves in upward direction, the spring will opposes the motion, so the spring force comes in the downward direction with the magnitude k2 into x1. Okay, so what's about this one? One more spring is shown here. So what's about the spring force or direction of the spring force? If I pull this one mass in downward direction, okay, this mass in downward direction, of course the spring get expanded and the resistance occurs in opposite direction. Okay, so spring get stretched, okay, spring expanded like this one, and the spring force comes in the opposite direction. Okay, so k1 into x will come here. Now if you just see the relation we obtained here, so for this one x is displacement with us, so x displacement already shown here. So what's about the relation between this one x displacement, this one theta? Simply we can get this relation. Okay, so what's about this one? This is nothing but the radius for the outer circle here. Okay, so this indicate the r2, this indicate the theta, this indicate the, okay, displacement already was just considered here x, so you can get that relation x equals to r2 into theta. Okay, so with respect to this one inner step, so the same actually displacement, angular displacement occur here theta. So this is the radius with us r1. Okay, and the displacement with us for the inner step is nothing but the, so what's about the linear displacement we are assume here x1. So with respect to this one, we can get x1 equals to r1 into theta. So if you just see the this relation x equals to r2 into theta, so what do we get here? X divided by r2 equals to theta, and in case of second relation x1 divided by r1 equals to theta. So simply if you just look towards the right side, theta is the same. Can we equate the left sides? So you can get here theta equals to x divided by r2 equals to x1 divided by r1, like this one. Or simply you can get the relation for this x1 as, if I take this r1 towards this side, r1 towards this side, what do we get here? x1 equals to x, this x will remain as it is, r1, okay, goes in numerator. So what do we get here? X1 equals to x into r1 by r2, like this. So if I differentiate this one twice time, so what do we get here? Theta double dot equals to the double derivative of this one, x double dot divided by r2. This we can get the term for this theta double dot. Similarly, if I differentiate this term with respect to timing twice time, then we can get this term in this way: x1 double dot equals to x double dot into r1 by r2. This term is constant, this will remain as it is. Now you can easily apply the Newton's second law of motion or D'Alembert's principle to get the differential equation. Now by using the Newton's second law of motion, you can easily develop the differential equation from Newton's second law of motion. Okay, so what's about the Newton's second law of motion here? Now focus carefully on the left side forces. Okay, so what's about the Newton's second law of motion? Accelerating force equals to summation of external forces. Okay, so look towards the accelerating forces carefully here. If you compare this problem with the previous cases, in the previous cases we found the accelerating force single force. Okay, so in this case look towards this accelerating force. So I theta double dot, okay, turns about this center, okay, in which direction? In anti-clockwise direction. So this force must be positive. So what's about this one? This actually turns about this point. So here is the center point. Okay, this turns about this point in anti-clockwise direction. So m1 into x double dot, okay, this is about the accelerating force multiplied by, so this actually turns about this point at a distance of, so radius is given here r2, so r2 multiplied by this force, r2 is here. What's about the next one? Next accelerating force, next accelerating force is here. So this also turns about this point in anti-clockwise direction. For anti-clockwise direction, give the plus sign in this way. So what's about the, sorry, this force actually must be here. Other things are correct. This one. So m2 x1 double dot. Okay. So what's about this one? What's about this distance? The distance with us r1. Okay. R1 equals to external forces. Now pick up one by one external forces. So here is the damper with us, spring with us, and another spring is here. Okay, so if we just focus on the anyone, this one, C x single dot, this is about the damping force, turns about this point in which direction? This one in clockwise direction. So to give the minus sign for this one, so minus sign for this one, you have to take the moment of this force about this point. So damping force multiplied by this one distance, so distance comes here r2. So what's about the next force? Next force is here k1 multiplied by x. Okay, this is about the spring force, spring force multiplied by distance. What's about the distance? So this radius with us r2. Okay, so what's about the next one? Next force with us, this one k2 multiplied by x1. So what's about this one? This force, if you just see the direction of this one force in clockwise direction, so give the minus sign for this one. So k2 multiplied by x1 multiplied by, what's about the distance? Distance with us r2, sorry, distance with us small, this one inner radius with us r1. So in this way we can get the differential equation. So rearrange some of the terms so that we can get this differential equation in simple form. Okay, so what's about the value for theta double dot? So already this relation with us. So why we need the this one theta double dot, the x single dot? If you look towards this one x1, okay, so this equation available with us in two variable. So my first aim is to get this equation in single variable. That's why first of all convert this one theta double dot into linear term. So that term already with us. Okay, so I into theta double dot. Theta double dot means here x double dot divided by this one r2, like this. Okay, this is about this term. Okay, this term plus next one m1 multiplied by x double dot into r2. This term will remain as it is. Okay, then next one with us m2 multiplied by So what's about this x1, x1 double dot, x1 double dot? Already this relation we have just get in terms of x here, x double dot into r2 divided by r2, like this one. This is about the x1 double dot. You can just convert this x1 also in x. Okay, so if you just see this equation, we can get in terms of only x. Okay, so multiply by this term, r1 equals to minus c into single dot, x into single dot, multiply by this r2 minus k into x multiply by r2 minus k2 into x1. So what's about this x1 term? x1 x1 term already with us here. X1 is nothing but x multiplied by r1 by r2. Okay, this is about the x1 term. X1 term is here. Okay, multiplied by r1. Now try to simplify this one like this one. I just take this x double dot common from all the terms, plus m1 into r2 plus m2 into r1 square divided by this r2 x double dot equals to minus c into x single dot into r2. Okay, minus next term. Try to simplify the next terms. Okay, so you can get the relation for the next by taking simply this x as common. If I take the minus sign as common, so instead of the bracket, k into r2 plus next one, now if you look towards this relation, k1 into x into r2 minus k2 into x into r1 by r2 into r1, so simply multiply by this r1 term to this r1. So what we get here? R1 square. Okay, take the minus sign common and this x common. Okay, from this side. So what's about the remaining term? K1 into r2 plus k2 into r1 multiplied by r1 is nothing but r1 square. This r2 will remain as it is, multiplied by this one x already we have taken common. Okay, so if you look towards this relation, okay, again you can just simplify this equation. So in the next step, the equation can be written like this one. Just take this 1 upon this one r2 as common. So instead of the bracket, this ip will remain. So ip plus this one m1. If I take this r2 as common, means you have to multiply by this r2 term by r2. So m1 into r2 square plus m2 into r1 square into x double dot, and simply take all this term towards the left side. So equation will be written like this one, c into r2. Okay, so the plus sign is given for this one, c into r2 into x single dot. Okay, plus this term. Okay, so k1 into r2 square. If I take this r2 towards this side, simply if I take the common r2 from this side, so r2 goes in the numerator and you have to just multiply by this r2 terms to these terms in this way. So c into x single dot, so r2 goes in numerator towards the right side, and r2 multiplied by r2 is nothing but r2 square. If I multiply by r2 term to this term, so r2 square will come here. Okay, so r2 multiply by here, r2 multiply by this r2, one r2 get cancelled, and the equation you can get like this one. Now if you look towards this equation carefully, so what's about this term, what's about this term, what's about this term? Simply this term indicate the mass term, this indicate, this term is nothing but the damping coefficient term. Okay, and what's about this one? This is nothing but the stiffness term. Okay, so we can write the simple form of this equation in this way: mx double dot, this term in the mass term, so we can simply write this one mx double dot plus c into x single dot. Okay, so this term indicate the damping coefficient and this term is nothing but the stiffness term. Okay, so k into x equals to 0. So what's about this mass? We assume this mass is nothing but this term. So simply write this term here: ip plus m1 r2 square plus m2 into r1 square. Okay, so what's about the value for this ip? Already given in the problem, 1.1 kilogram meter square. So 1.1 plus what's about the value for m1? M1 with us 10 kilograms. So 10 multiplied by what's about the radius r2? 30 centimeter with us. Convert this one into meter. So you can get this one 0.3 square plus next one mass m2 with us 25, r1 with us 0.1. Okay, so simply substitute all the values and get the value for this one mass. So what's about the next one? So next with us this one c is nothing but c r2 square. Just substitute the value for this one r2. Our target is to find out the value for c. Okay, so this term is nothing but the damping coefficient term. Don't cancel here the c with the c. Okay, so this c represent the total damping coefficient involved in the system. Okay, so c multiplied by this one 0.3 square of this one, so we can get 0.09 into c. So what's about the k? So this term indicate the k term. Okay, so k with us k1 into r2 square plus k2 into r1 square. Substitute the value for k1 r2 k2 r1. Okay, and solve this. We can get 1900. Okay, like this one. Now equation number a to represent critically damp, okay, system. Okay, so what's about the meaning for this one here? To represent this equation a to be critical damp system. Okay, so simply actual damping coefficient must be equals to critical damping coefficient. So we know the value for this one cc is nothing but here. What's about the cc? For critical damping coefficient, we know this relation for the linear system: 2 into square root of k into m. Now if you look towards this one, so what's about this one? This first term, this one c term with us already, this one simplified by us here 0.9 c. Okay, just substitute here 0.09 c. So what's about the towards the right side? 2 into square root of k with us 1900. Already we have solved this one 1900 multiplied by the mass term with us 2.25. Just substitute here. Just simplify this one. We can get the value for this one c equals to this one 1452.996 Newton second per meter. I hope in the today's lecture the problem discussed related with the spring, mass and damper system clear to you. Thank you.